All right, everybody, welcome to week 6. And this week we are going to be talking about the movement of water through soil. But first, I did want to do a quick review of bulk density and porosity. There's a little bit of confusion on density and bulk density. It's a confusing topic. So I wanted to just do a little quick review and maybe hopefully a bit more of an explainer here. So going back to our idealized soil here, we have a soil that is about 50% solids and 50% space. Of that space, we have about 25% pores and 25% that's full of liquid. Now, we only want to be measuring the density of the solids, not necessarily of other things. We just want to know the bulk density of soil, the amount of soil per unit of total space. So what we do is we air dry or oven dry, our bulk density pores, and then all of that water evaporates. And we know that it's about all of that space becomes pores. So 50% pores, it's just full of air. So to review, density is mass divided by volume. So when we talk about that in terms of bulk density, we are talking about the total mass of both the mass of both pieces, both the solid and the pores, divided by that total volume. So we have, again, the mass of the solids and the volume of the solids, that's here. And then we have the mass of the pores and the volume of the pores. Now, the mass of the pores is actually 0. That has no weight, it's full of air. So that gets eliminated. So that means that bulk density is the mass of the solids divided by the volume of the solids plus the volume of the pores, or we could just call that the total volume that's here. Porosity, if you recall, is the volume of the pores, this part, over the total volume. And so we usually express that either as a percent or as a proportion of the whole, which would be in the decimal format. So in soil, water and porosity are related to one another, and they're kind of, we can think of them along this spectrum. So on the wetter end of the spectrum, we have saturation. So at saturation, all of the pores are full of water. Every single pore within the soil is full of water. You can see that that means that any more soil or water that's coming into the soil is going to be lost. It's going to be drained out. We are full saturation. Just below that, in terms of wetness, is field capacity. Now, when we're talking about field capacity, only the small and medium pores are full of water. The large pores have drained. And then the driest would be the permanent wilting point. And so at permanent wilting point, only the smallest pores still contain water here. And that would be kind of the drier end of the spectrum. So you can see that not all pores are created equal in terms of their ability to hold water. The first ones to drain are the big ones, and the smallest ones are the last ones to drain. So when we talk about a desirable characteristic of soils in terms of water capacity, we want the soils to hold on to water, but not too tight. And it's this balancing act between your field capacity and your permanent wilting point. So field capacity is the ability of the soil to hold water against gravity. This is, in absence of anything else, this is the maximum amount of water that a soil can hold. Whereas permanent wilting point is the ability of soil to hold water against plant uptake. That is, this water that is held within these small pores is so kind of occluded and hard to reach that plant roots can no longer suction that up. And so there is kind of this balance between these two. We want the amount of water we have to be somewhere between those two things. Now, the difference between those two things is called plant available water. Plant available water is, in a technical sense, the field capacity minus the permanent wilting point. Now, that amount of plant available water differs by soil texture. So here we have this gradient of soil texture. We have sand, which would be the coarser soil, and then down at this end we have clay, which is the finest grained soil, and we have our loams in the middle here, of course. Now, starting down here with sand, we'll start with field capacity. Now, sand, remember, sand has lots of large pores, and so those large pores are the first ones to drain when we talk about field capacity. So a sand doesn't hold much water against gravity, and so very little of the soil water is held. However, sand also doesn't have very many small pores to hold water against plants. So it has very little, it doesn't have a hold on to a lot of water that plants can't get. You see about 5% here. So what that means is down here, sand doesn't actually end up having a lot of plant available water. I think this is something that we all kind of intuitively know. At the other end of the spectrum, we have clay. Now, clay has lots and lots of tiny little pores. And so those pores are really good at holding on to water. And so that means that there's a lot of hygroscopic water. Even though a clay might have a lot of water in it, plants can't get at it here. But because of those so many pores, a clay can actually hold on to a lot of water against gravity, which again is that field capacity. Now, loams are kind of in the middle here, and those are kind of, we'll call them the ideal soil in terms of water availability. They're not too heavy, not too coarse, and they hold a lot of water. So you see that right here. Now, of course, why does this happen? This is the important thing to understand about water movement in soil, is why this happens. And so there are kind of a couple different forces at play here when we talk about water retention. So the first one is cohesion. This is a specific property of water. So cohesion is when water molecules stick to other water molecules. Now, just as a reminder, we have a water molecule that's H2O, and the oxygen is negatively charged, and then we have these two H+ ions that are positively charged. So what that means is that water has a slightly negatively charged end here, and then it has two slightly positively charged things. They're called dipoles. So when a water molecule is next to another water molecule, it can start to be slightly attracted to the opposite end of the other water molecule. So we have here this positive dipole is attracted to the negative dipole of this other water molecule via, if you recall, van der Waals forces from your intro chemistry class. And it can be attracted to at least one other molecule, several others at the same time. There's not really, a restriction on that. Now, this cohesion, this is why we get things like water droplets, or if you spill water on a table or something like that. Cohesion is what causes water to bead and causes it to stick together. It also gives us things like surface tension. Another property of water is called adhesion. Now, adhesion is when water molecules stick to surfaces. So in our specific case here, we're in a soils class. So we'll talk about it in terms of how it sticks to a soil particle. Remember, soil particles are slightly negatively charged, right? That they have cation exchange capacity because they are negatively charged, and that CEC comes from isomorphous substitution. Now, because it's usually negatively charged, those positive ends of those water molecules are again attracted to the soil surface via van der Waals forces. Now, I know we're talking about cohesion and adhesion as two different things, but they can definitely be happening at the same time. So you can have two water molecules that are, that are slightly attracted to the soil particle, but then they're also kind of cohering to one another. So you have adhesion and cohesion happening both simultaneously in the same water molecule. Now, this has implications for the movement of water through soil. So returning back to our soil particle, right, the negatively charged end of it, when we have water that's moving past that soil particle, what happens is eventually some of it sticks to it, right? It adheres. Then once that water molecule is stuck to it, you have another water molecule that's then in turn cohering to that molecule. Now, this property is why you get things like your meniscus, right? So when you are in lab and you are measuring something in your graduated cylinder, the edges of that graduated cylinder are curved upwards. And that's because the water is both adhering to the side of that graduated cylinder and then cohering to one another. But in the middle of that graduated cylinder, there's not as much adhering, and so it's flat. Now, in soils, when we have the simultaneous cohering and adhering happening here to the soil particle, we can get lots of water molecules that can flow right past it, right? They're not all necessarily going to stick there, and that means when we have things like a large pore, that water molecules can move fairly easily through it, right? They can drain or something like that. However, when there's another soil particle close by, say as in a small or medium-sized pore, what ends up happening is that soil particle that is again negatively charged has its own water molecules that are stuck to it, that are adhering to that surface. And in turn, that water molecule can be attracted to the positive end of another water molecule. So on net, what happens is you get this network of water molecules that are attracted to one another and don't really want to move very many places. And so you get less water movement in smaller pores because of this adhesion and cohesion of the molecules within the pores. So when we talk about water movement within a soil, the first thing to note is that water moves from areas of high water content to areas of low water content. We see this happen all the time in our lives. If you spill water and you need to mop it up with a paper towel, you touch the paper towel to the water, and that water, as soon as it's in the paper towel, moves across the paper towel, right? The wetting area is more than just that drop of water that you need to wipe up. And that's because water is moving from the areas of high water content, the wettest areas, to the driest. Now that, until it reaches some sort of equilibrium. I think this is something that is somewhat intuitive, and we see lots of examples of that in our everyday life. In soil, it's a similar thing. When we have a wet area, that water moves to a drier area until it reaches some sort of equilibrium. Now, how to decide where that equilibrium is? Well, there's a soil textural component to this. So here's maybe two contrasting examples for when we add water to a soil. So here on the left, we have a sandy soil, which again, a sandy soil is full of lots of large pores. So when we add water to a sandy soil, first off, it infiltrates, or it comes into the soil really quickly and it moves. So you can see here this blue, darker blue here is where the water is at 15 minutes. This lighter blue is where the water is at 40 minutes. Green is 1 hour, and this outermost is 24 hours. Now, let's contrast that with a clay soil, which has lots and lots of small pores. The first darkest blue here is the water movement within 4 hours. Then we have here water movement within 24 hours, and then out here water movement within 48 hours. Now, a couple things to note here. First off, gravity is acting on this soil kind of the same amount, this water movement, the same amount. It's getting down to a pretty similar depth here. However, when we look at the sandy soil, it's not a very wide spread, right? We have 12 inches of spread each way for that water. Whereas clay, those small pores make for lots of lateral water movement here. We see that it's at least twice as far as it was in sand. That's because, gravity is the primary agent here, and there's lots of that water movement across pores. We call it capillary water movement or capillary rise. So it's able to resist gravity a little bit more. You can also note the time difference. So 24 hours here, it gets down to 72 inches in depth, whereas 24 hours for the clay soil, you're only at about 36 inches in depth. So there's a lot of different things going on here that we can think about, or that we can glean from this illustration. But this is fundamentally demonstrating the tension between gravity acting in soil water movement and adhesion. So in sandy soils, gravity predominates, and you see that it goes mainly just downward and it goes faster. In clay soil, you have both gravity and adhesion happening, but it moves down slower. Gravity is not winning as easily, and adhesion causes it to move outwards from an area of high water content to areas of lower water content to the dry soil around it. Now, of course, water can move into soil as well. That movement is called infiltration. So a couple things. Similar to water movement within soil, drier soils tend to have better infiltration. You think about it, when water is coming down, say as a raindrop or something like that, that has a high water content. It's wet. So if the soil's dry, it's it's more ready to absorb that water. People say that the soil's thirsty or something like that often. Another thing that is kind of being illustrated here in this animation is that larger pores tend to increase the amount of infiltration. If you see here, this is up top, and you have a lot of small pores, and not a lot of water is actually making it into these pores when all is told. However, when we have these larger pores, you can see that more water can flow into those more quickly, and it has the ability to get further down within those aggregates. So this is a demonstration of how porosity, and specifically the size of the pores in that porosity, can alter and essentially increase infiltration. Now, the reason that a lot of this happens is because of soil structure. Now, when we talk about soil structure, there's a couple of different components, but the most important one here is going to be aggregates. Now, aggregates are little clumps of soil particles, and you can see in this picture some examples of it. You see that these aggregates can come in different shapes and sizes. So here we've got a pretty big one, it's kind of round looking. Here we've got one that's long and thin. You have this one that's maybe a little bit more oblong shaped. Now, aggregation can happen for lots of different reasons, but one of the main ones, or I shouldn't say one of the main ones, but the one that's demonstrated here is from roots. So you can see that those roots are creating aggregates along the length of that. You can see they're held on pretty tightly. They're not going anywhere. So those roots start the aggregation process, and they skip the soil to clump. Maybe to look at a side-by-side comparison of these aggregates, on the left here, we have an example of pore aggregation. You can see that all the particles are pretty small, and there's not very many clumps of them. However, on the right here, we have an example of good aggregation. You can see that there's lots and lots of clumps, and that those clumps have many different shapes and sizes. Now, when we have a soil with good structure, this also alters the water holding capacity. So you can see that if these clumps of soils are really close together and the particles are jammed together, there's not very much pore size, and so the soil can't hold very much water on net. However, as they get a little bit further apart, those soil particles, and say dispersed in an aggregate, there might have been a root coming through here or something, you can see that water holding capacity goes up. There's just more water to hold in here, right? The surface area here, you get lots of adhesion and cohesion within those pores of a well-structured soil. Now, an important thing to note, when we're talking about things like water holding capacity or plant available water or infiltration, there is both a soil textural component to this and a land use and management component to this. Soil texture kind of dictates the set point of soil. Soil texture isn't something that changes very readily, so we can't alter it. It's pretty static. However, land use and management is a dynamic. And so for each of these properties, there's kind of a tendency of a specific soil from its texture, but then we also have some degree of control over it using land use and management. Now, just to kind of illustrate this, this is a technique called called microtomography, and we have one of the pioneers of this in soil here at Mizzou, Dr. Anderson, and this is in fact a paper of his where you go out and they take a bulk density core and then they image it. And these red dots here are demonstrating the pores. So here we have kind of an annual row crop agriculture, lots of tillage, things like that, lots of soil disturbance. And you can see that there's lots of little pores. There's, but they're kind of dispersed, et cetera. They're not very well connected to each other. But when you start to introduce animals in this system, it's still somewhat annual, but you have these animals, you see a couple things happen. One, there's so many more pores. You can see them here. And there's bigger ones, there's smaller ones, but then they're also well connected to one another. So that for when we talk about water movement, obviously water is able to move through a larger pore like this a little bit better, and you have more pores to hold water just generally. Here we have the last kind of management they've used is a perennial like grafting. So perennial meaning that these plants come back as the same plants year after year after year, and they're not disturbing the soil or anything like that. And you can see that there's lots of more pores, lots and lots of pores here. They're pretty well connected. There's not a lot of really big pores, but they're small to medium sized pores. So with this, if we were to be looking at this and guessing, we would say that this one probably has more pores than this. Both of these have more pores than the annual, but this one probably has a greater water holding capacity and a greater field capacity, simply because it has more of the small and medium sized pores than this. This has more large pores that would probably drain against gravity. So just a quick review. When we talk about porosity, which is porosity is inversely related to bulk density. And when we have more porosity, we have a greater potential for that soil to hold water. However, that's just potential. That does not say a lot about the actual ability to hold water. And the actual ability for a soil to hold water is this fight between gravity and adhesion. Adhesion, again, is water molecules sticking to the surface of the soil. So we have field capacity, which is the amount of water that can be held against gravity. This is when gravity and adhesion are at an impasse. So this is a specific water content for each soil that varies by soil texture. Permanent wilting point, or just wilting point, is the amount of water that can be held against plant uptake, hygroscopic water. So this is the water that's held in super duper tiny pores. And so plant roots can't actually get enough suction to get that water into the roots and take it up. But there's still some water there. So this is called the permanent wilting point. Again, something like a clay would have a higher amount of hygroscopic water, and a sand would have less. Remember that plant available water is the field capacity of the soil minus the wilting point of the soil. These are both water contents in terms of grams of water per gram of soil. And so the difference between those, the delta, if you will, is the plant available water. Soil water movement into soil, which is called infiltration, within soil, and also when it leaves, with leaching, all of those things can be influenced by soil structure. Soil texture plays a big role, but as kind of a set point, but then soil structure can also play a big hand. And when we talk about soil structure, most of the time, what we're talking about is aggregation, or how well clumped those soil particles are. Soil structure is a dynamic property of soil that is often responsive to land use and management. And so we looked at images of using microtomography from one of Dr. Anderson's papers, and it showed, perennial crops, grasses specifically, had more pores, and that's presumably due to the greater soil structure. All right, that's it for now, and look forward to seeing you in lab this week.